What's up, everybody? It is cold up here. I got Batman just, yeah. Oh, and we got, oh no. Multiple audio. There we go. Grace, good to see you there. What should we do? What assignment should we do? It's so cold. It's so cold. I had a snack. What should we do? Which My Pearson question are we going to do? St. Patty's Chapter 8 quiz. Which question on Chapter 8 quiz? Which question? Which question? Drop the question. Let's do it. Might be able to do all of them. All of them? Let's do it. Megan, let me throw you some 5,000 points. We can do all of them. I think we have enough time. Do all of them. Oh, I'm just like, I think I'm going through caffeine withdrawal. It's bad. I've got myself addicted. A student who has created. There we go. We got the first one. Soraya, good to see you. Did you have a good break, Soraya? Megan, did you have a good break? Grace, you have a good break? Is Mubot not giving out points? Mubot, give out some points. Mubot, give some points out. We're about to hit the downhill on the class, where we will be, less work. You had to work? Oh, no. I'm sorry to hear that. It's, a little money. That can be good. Last Thursday. It was your birthday. Happy birthday, Zariah. Congratulations. That's great to hear. Why does the thing have extra? I feel like they redid this. Let me click it again, then we'll jump into this. Okay, that looks better. What? This window's being weird. Okay. We're just going to roll with it. Let's do it. You're welcome. All right. Let's go. Go check it out. It's being weird. It's got this white space up there, which I'm like, come on, don't do that. Can I do this? Helps a little bit. Let's get the question people want. And we saved the class details, office hours, and we're going to find that question. The question is, a student who has created. Okay. Oh, there's 17 questions. That one's a very common one to do. Cell phone usage. Okay, we'll grab that one next. Okay. So we got, and just keep dropping your questions right here. I've got cell phone usage, and this one is, and that's the way to do it. Just drop the first few words of it. A student who has created. This one will be pretty quick, I think. I like it. Okay, let me get the first start of this. It is 6:33. Stat Tool 1, Chapter 10, quiz. Oh, Chapter 8 quiz. What am I doing? Why are we here? Okay. We are good to go. If I could paste right. Okay. So on this first question right here, we are looking at a student has created a linear model, is disappointed to find that their R squared, that's what that value is called, is very low at 13%. So what does R squared mean? R squared is the percent of variation in Y explained by the variation in X. Mubot's about to drop it in the chat. That's an important thing to know. And when we think about the way R squared looks, we're going to pull up a little bit of notes here because we always have to have some notes. R squared is kind of like correlation, but it's not correlation. These are the notes. If you're watching this question, the notes you need to understand to have a deeper understanding of what this topic is. Why is SpongeBob here? I don't even know. I remember when I pulled that up. Oh, because I said I want to rock. I want to rock. Rock. Okay. So the way R squared looks is R squared can go from 0 to 1. R squared of 0 could look two ways. It generally looks like this. But in truth, there is the R squared of 0 when the line does not explain anything. Because the linear model works when there's a linear relationship. So this would still be an R squared of 0. Now, the higher the R squared gets, it doesn't really matter if it's positive or negative. You could see right here at 0.5, it could look something like this. And that'd be 50% of the variation in Y, explained by the variation in X. And you could just make it go down. Now, when it's 1, it would have to be that the line perfectly explains. So you'd have to have a line. It could go down, or it could go up. and then all the points would have to be on the line as best I can draw. All the points are on the line. And then the line explains all the variation. R squared of basically 1. We'll do about 1, like about 1. So the R squared of 1 is when the line perfectly explains everything, and an R squared of 0.5 means 50% of the variation in the data. You can see like here there's still misses, like there's still residuals by how far it is away. And then this is when it explains nothing. The line explains none of the variation, as does a model that is improperly fit to nonlinear data. So what do we have? SpongeBob right there chilling out. Does this mean that the linear model is not appropriate? It means it has a very weak relationship. That's what I would say as a statistical person. Whether or not the linear model is appropriate, we have to look at the scatter plot. So there is no value of R squared that must be met in order for it to be appropriate. Determining whether the linear model is appropriate involves understanding the context. That's kind of true. The linear model is typically preferred because of no. I believe it's this one. A little weird wording. I think that's going to be it. Does the model allow the student to make accurate predictions? No, not really. I would say no, not really, because it's very low R squared. No, a low value of R squared indicates that there's a large amount of variation around the regression line, which implies that the accuracy of the predictions is difficult. We should get it right. I got a little bit scared on this one because I have to use their answers, and an R squared of only 12% would mean we don't know if the model goes up or down because R squared does not include direction like correlation does. So the model could go down, and it would mean that we only have this line right here. Sure, that's all right. This line only explains 12% of the variation. And so there's a lot of large misses, like we don't. But also what they're saying about, is it an appropriate model? We don't know. There could be some weird bend in the data. Like this data right here has a bit of nonlinearity to it. So I wish they said you should investigate a scatter plot, because now maybe the line does this. But if you look at this relationship, it has a sort of nonlinear relationship. It kind of flattens out. So the R squared does not attest the appropriateness of the linear model. It does not test that. The R squared only tells you the percent of variation Y explained by the variation X. So good question. We only have one more question. Drop some more questions. We got the cell phone usage. So what are we going to do after cell phone usage? What question are we going to do after cell phone usage? Regression of total value. Yeah, I got these right here. Thank you, Megan. And you can drop these at any time. Don't worry if I'm doing a question. You can drop these, and then we'll put them in the order. Okay. Gallup poll about annual smoking. Grabbing the questions here real quick. You can drop these at any time. I'm going to write Gallup smoking. I can't grab it. Gallup smoking 100 years ago. 100 years ago. And any evidence, animal and gas. Oh, gestation period. Animals and gestation, that one. And 100 years ago. Okay, we now have a list of questions. I love it. And oh, yeah. Good work right there, animals. Yeah. Okay. So let's go find the cell phone usage question. There's 100 years ago. And if you see your number, you can also tell me the number after I write down the question. You're like, Brian, go to this question. I'm looking for cell phone usage. Oh, wait, is this it? Is this the cell phone? Is it a little short one? Okay. I think it's this one, right? Okay. So here's the cell phone usage question. We got institution. You got it. A correlation between cell phones usage and life expectancy is very high. Should we buy cell phones to help people live longer? Don't even read their answers. Don't read their answers. What do you think's going? Don't read the answers. What do you think's going on right here? What do we call it when you have, variables where it's like cell phone usage and longer life? What do we call this where it's like your cell phone usage and life expectancy? It's like, oh, if you buy more cell phones, you live longer. If you live longer, you buy more cell phones. So we can't say causation exactly. Correlation is not causation. Boom. Classic thing in statistics. Also, this is where you have X and you have Y, but there could be some Z variable. And the Z variable is probably money. Does that make sense? I would say there's probably we call it a lurking variable. So that's a key word to know that they're probably going to throw into this. Exactly. Lurking Lurking variables are variables outside the XY relationship, which could be the real background variable. Like probably money is why people buy cell phones, and money is why people live longer. So overall, it's probably if we look for lurking variable, we can find it. So I would bet lurking variable. Is there no lurking variable in here? Lurking variable. I'm just going to take and say, is it? Yeah, look at that. I didn't even read it. I just look for a lurking variable. It's probably that there's a lurking variable, which is probably money. It doesn't even explicitly say money, but a lurking variable means a variable outside of the XY paradigm. Paradigm being the relationship the two variables have. Like, it is true that if you own more cell phones, you live longer. It's true that if you live longer, you own more cell phones. But it's probably some variable external to these, and we also can't say correlation is causation, which I wish they also said in this problem too. Like you wouldn't want to say it causes people to live longer. We don't like that cause word around here. We don't say cause. I think this was at 12 minutes. I wish we could check our answers after each question too. I know, right? I get that benefit. An institution reports many demographics. Thank you, Megan. And thank you, people, for being here. Thank you, everybody, for being here. It's really awesome. I like getting these done and then knowing students have them done because then you're like, get some hundreds. Regression. I think this is one of the early ones. Is this the one someone wanted? Regression of total revenue on ticket sales. There's two versions of this. So we may have to do both versions. I think it's these two. So this is a concert production company. Is this the one people wanted where it says regression of total revenue on ticket sales? I think this is the one. Someone confirm. This is it. This is it. Okay, a concert production company. There's two versions of this. So we'll put both in here and we'll put both versions. Oh, wait, is it not? Oh, then let me redo. Okay, let's find it. Regression. Oh, this one, right? This one. Oh, so it does say this. Okay. Okay, you are correct. Let's do it. Okay. I'm going to copy paste the start of the things into these. So, oh my God, I just deleted it, but I can Control Z that. So I think it's this one, right? Yeah, I think it's. Yeah, we could do both of those next. We'll do that. You got it, Matthew. Thank you for being here, Matthew. Let's raise some points. Okay, so we are currently at. If you're wondering what I'm doing in the background, I'm literally just going in here and like marking everything so that way we can like. That's what I do when you give me the questions. So that way I can just go in here and timestamp it. So we're at 16:03. Okay, so here we are, and we need to figure out some regression stuff. First thing you need to look at here with this is you need to know the what and the what. First thing you need to know, if you see a regression equation like this, you need to be able to identify what and what. What are the values here called? You need to know what this equation is. You need to know how to read it. So if you're doing this problem, you should know what this equation means. We try to review here. What does this equation mean? Yeah, this is the B0, which is the intercept. This is the B1, which is the slope. This is the name of the X variable. This is the name of the Y, predicted Y. So that's predicted Y. So this is the prediction from the model. And this is the explanatory variable. So the predicted, the response variable. So you could say the response variable. But understanding this right here, that Y hat equals B0 plus B1 times X. So understanding that classic interpretation, Megan, great job right there. And so what's it going to ask us to do? It says first, we are trying to do it for a 10,000 seat venue. So all we're going to do is go right here to the ticket sales and just drop 10,000 into this. We're just going to drop 10,000 in, multiply out. So just solve the equation. 10,000 times 31.85. Subtract from it 8439, and there's the number. Once again, we're just plugging 10,000 in, solving out. And so there's the expected revenue. Now, would it be unwise to do this? Why or why not? So the answer lies in the data they collected. And what are we doing? So we are using this model to predict at 10,000. It's way far out. So this is called a what of your model. This is called a what of your model. When you go beyond the X or even just the highest value of X, you are whatting. Going outside the scope of your X, the lowest counts 2. This is the scope of the X, the boundaries of the X, the scope of the X. You are extrapolating. So you are extrapolating way beyond your model's things. So this would be an extrapolation down here of the model. This would be an extrapolation outside of here. Within the scope of the X is where the model understands what's going on. You couldn't predict for like a little like house party or whatever. You can't predict for a huge venue. I mean, you can mathematically do it, but should you? No, because you're extrapolating well outside the model. So we just look for the word extrapolation, and there it is. There's extrapolation, and we wouldn't want to do that. So that would be, we shouldn't, the model is not meant to predict. It wasn't created from data that would understand that region of the space of the X. The model really only understands where we have X values. So the model is meant to predict in that area, not outside of the scope of the X, which does include lower. A lot of people forget that a lot of times. And I will say this, we've never put this on a test. It's been on advanced tests before. If your data looks like this right here, then a lot of people will argue that extrapolation can occur within this region. So extrapolation is where you don't have X values. So since your data is kind of limited to these regions, people might say you're extrapolating what your model does in that region where you're missing a lot of data. And obviously you'd be like, well, we don't have data right there, but this is a minor amount of extrapolation. You don't want to extrapolate big parts of your X regions. So we wouldn't, that's actually a big thing in industry. It's like, wait, make sure you get some middle points. A lot of industry work right there. Okay, Gallup smoke. Oh, what should we do? Let's throw these other two in here real quick. A concert production company. I think people wanted both of these. It depends on, so that goes, and Zariah, really good question right here. It's, don't worry, that won't be on the 201 test. But if you had data that looked like this, Zariah, where there's a big gap, a lot of people will argue that your model is extrapolating here. Does that make sense? It depends on how big the gap is. Like, I'll show you, like, that is, I would call that an extrapolation of the model in between because there's no X data. You're still extrapolating, not so much. Now you're not extrapolating. At this point, you have enough data to really nail down the model. So at this point, I would say even here, you're not extrapolating really. Not minor, moderate, major. At that point, I would argue there's an extrapolation. There's an extrapolation now. Depends on how big the gap is, not on the 201 test. And then let's try defitting the regression line. Oh, nice. I like it. Okay, we're going to throw, say yes or no. Should we throw both these? I will take, if there's a yes, I'll do them. Should we throw both these in real quick? I've got an analyst tried. We'll throw that one to the list. Yes or no? Should we throw in both these ones right here? If there's a yes, we'll do them. Or if there's silence, we won't. Going. Yes. Okay, Megan says yes. Okay. Let me take the start of this, a concert production. We're going to do both these, both versions. Okay. Thank you, everyone, for being here. Manic, good to see you. Okay. We are getting the questions ready. And remember, it's about learning the concepts. That's why we teach these things. So you'll notice I usually go in more depth than just telling you the answers. So if you're watching this right now, think about the concepts we're about to go over right here. Let me ask you, when we visualize a regression, we always add it to a what? When we visualize a regression, we always add it to a what? What is this graphic called that we are adding the regression models to? When we visualize a regression, we always add it to a what? A scatterplot. The scatterplot is the visualization of two quantitative variables. So a scatterplot is the visualization of two quantitative variables. Now, these concert production ones are kind of similar as we do them. You'll notice here the smaller venue has a scope going from about here to here of the x's. The larger venue has a scope, and we're just kind of marking the scope of the x's, rather. The scope goes to there. It's the highest point on the x's. We'll go more specific. There we go. And then also what you'll notice is the variation around the higher model is more variation. They'll probably mention that in this problem or the other one. And here's the lower model with less variation. So this is the smaller venue, small venue in blue, and this is the large venue in red right there. That is horrible, and that's the smallest I can write. So small venue, blue, large venue, red, larger distance on talent cost, similar slope to the lines, but there is more variation around the big model. So let's see what they ask. Does the relationship between talent cost and total revenue describe it? Well, it's positive. So It's a strong positive. There's one outlier. Is that the one towards the end? Sure. I think it's definitely positive. So we have weak positive. I'm going to go with strong positive. I'm a little scared, but we're going to go strong positive. How are the results of the two venues similar? Both venues show that higher talent costs. Cause? No, we don't want cause. Cause is a bad word in stats because correlation is not causation. It's a bad word. You see cause or prove. We don't say that around here. That's one of those teaching to the test moments. We don't cause or prove things here. So both venues show an increase in revenue associated with talent costs. It's a little iffy. I'm going to go with this because I think it's strong. It's not weak. The reason I think it's strong is if you draw around these, you generally see a pretty tight relationship. That's not weak. Neither of these are that weak. They're kind of compact. They're moderately strong. So I think they're going with that being a slight outlier, or that one. It's the whole outlier thing is a little nuanced. It's what is an outlier? It depends. We have ways of measuring it statistically, though, which they're not doing here. There is ways we could mathematically measure it. How are they different? So which one has more variability, the large or the small venue? Which one has more variability, bigger errors, the large or the small? Which one has more variability? The large one, exactly. We can see this here visually now that the large has more variability and the small one has less variability. So the larger venue has greater variability. The revenue for that venue is more difficult to predict because it has more variability. It'd be harder to predict. We should get 100. Yep, there we go. Little scared. Don't be scared. And here we are with the other one. So same sort of idea. I think it's the same data. Virtually the same. If you notice, I'm just going to keep this graphic up here because all they did was separate it a little bit more. It looks nearly identical. You can see the same positive relationship. It's virtually identical data. I don't know why they made two separate graphics, but you still have a positive relationship here and positive relationship there. And then apparently after a certain amount of ticket sales, they move it to the large venue. So describe the relationship. It is definitely strong positive. Well, you know it's positive. Strong, and if you're wondering why it's strong, actually, this one's a little more obvious in my opinion. I'll draw it. The strength of the relationship is how tight it is. So when you draw around this, that one's pretty strong, that one's pretty strong, and the linear models would be this. Come on, snap, there we go. And the linear models would be this. So pretty strong positive linear relationships. And so we would go with that. Or are they saying there's no outliers in this one? Strong positive. There's no outliers. Sure. How are the two venues similar? Oh, it's basically the same question. Both venues, we don't say the quasi word. So both venues show an increase is associated with an increase in the other. How are they different? The large venue has... Is it the same question, basically? Making it harder. The large venue has more... Large venue has greater availability. Venues for they'd be harder to predict. Wait. Oh, man. The larger venue populates a higher magnitude region of the plot than the smaller. I guess maybe they are similar in there. That is, because now here you see the large venue has greater variability. Revenue for that venue is harder to predict. So B is wrong there. The smaller venue has greater variability. Revenue for that, see, this is just the reverse. If this is easier and this is harder, they can't both be correct. So that's just logically impossible. The larger venue populates a lower variability, which it doesn't. They're talking about the magnitude, the range of the X's. So clearly it's that. Yeah. I don't love that one. And they're kind of, it's arguable about the variability on this. It's arguable. I wish they gave us the data because I'd analyze that data. Well, we got both of those done. We're going to do some Gallup smoking. Gallup smoking. Look at all the ones we're getting done. We could do 100 years ago since we found that one. We'll find them and we'll do them here. So 100 years ago. I think this one actually gives us the data. And is there any evidence? Yeah, let's do that one next here. So Matthew, good question. We got that one on the list. I think this one we need the regression solver. Wait a minute. Let me double check. Do we need to? We do. So for this question, you need the regression solver. The regression solver can be found under the modules. So you got it, Matthew. Under the modules, scroll down. Where's modules? Modules? There we go. Under the modules, scroll down and let the page reload on you till you get to Regression Solver Pro. Go ahead and download the Regression Solver Pro. Download the Regression Solver Pro. Open it up on your computer. If we have you do a question like this, there are things you would do on the test and things you wouldn't do on the test. We will never make you solve for the coefficients by hand. So what we do here is, enable edit, okay. What we do is we give you the solver where you can either input the statistics like the correlation, the standard deviation, all this good jazz, or you could put in the data. Do not put it here on the X and the Y, put the data down here under the data. So on this problem, you would go to the data and go to here and copy to clipboard. Now, hit Control-C or Command-C. Now, go into Excel, and I like to paste it over here on the side. Now, we want to predict the average speed, and I want to double-check the problem first. It is that we are just entering in the year. So if you look at the plots, I think it'll show it too. Up here, they do have 1900 on the plot, year 1900. So we're going to grab 1900, or the year, and put this in. We're going to scroll all the way down, hold Shift, Control-C or Command-C, then go over here to the X variable, make sure to only paste in the yellow, and paste those years. Now, click the average speed, scroll down, hit Shift, and Control-C or Command-C to copy, and then go back to Y and paste it in, and boom, you get everything. So if you notice, put in the X, put in the Y, make sure you do the right ones. X is the explanatory, Y is the response. We want to predict average miles per hour. You can change that, you don't need to, because it's just the Y variable of interest. And the X variable is year. Year explains the average mile per hour. So with this in mind, we now have the intercept right here. I think we can just copy paste this. Let's bring it down here. There we go, and it says to 2 decimals. So there's that, and then we go back and we grab the slope coefficient, which is B1, and the slope coefficient goes right there, and it says to 2 decimals, so we do that. We now have the equation. So first, let's figure out where the data's at. Now, is there a sudden drop at the end of the data? Do you see how this has a drop, this has a drop, this has a drop in the last like 5 years? Is there a sudden drop at the end of the data? Look at the last 5 years. Does it suddenly drop off? And what do we mean by drop off? We mean it drops down to like the 30s. Like not 39. We're talking like 28 and something. During the last 5 years, yes or no, does it drop to like the mid-20s, the upper 20s, lower 30s? Does it suddenly drop? During the last 5 years of the data, yes or no, does it suddenly drop? During the last 5 years, 1, 2, 3, 4, 5. Or does it stay around 40? Who says yes? It's not really. No, it's around 40, right? Well, which of these graphics makes sense then? If during the last part of the data, it doesn't, which one of these makes sense? A, B, C, or D? So, and I'm on Top Chat. Which of these graphics now makes sense here? Which of these graphics makes sense? The first one is, yeah, it's graphic A. So there we go. Because it doesn't have a sudden drop. If you look at the data, it doesn't go down to 30 or doesn't go to the high 20s. No. So it's got to be this. Now, also, if you look at the data, you will see there's gaps where the world wars happened. So you see right in there in 1915 or so. Another gap right in here. So you can see gaps in the data. And this also has gaps. There's the gaps where World War I would be. There's the gaps World War II. And I think this is actual real data. So they're showing you it's kind of leveled off on the miles per hour. So it's gone up. A little bit of non-linearity. Hopefully that doesn't come to bite us in answering questions. Very linear there. Piecewise regression would be great. So correct. We don't need all the years. Correct. Because sometimes you miss years. Yeah. There is a positive relationship with, let's see. There is a general linear trend. Oh, wait. There is a general linear trend with no races between this and this. So we have to acknowledge that. So there is positive, I would say moderate. There's general linear. It generally goes up. There is a little bit of nonlinearity. There's something about this question, though, that I need to double check. I think we're good on this. So there are gaps in the data, and it's generally linear. Are the conditions for regression met? Now, this is where I think we say no. Let me double check. I think this is where we say no. The relationship is not straight enough in the early part of the 20th century to fit a regression line. The variables are quantitative and there are no real outliers. So if we look at the plot, what they're getting at is if you fit your regression model, if you notice here, there's especially that's nonlinear. So as in, it doesn't go around the line. Even if you put a line straight through this data, which is the point of a line, if you put it straight through the data, you can see the bend, you can see this. So that's what it's getting at right there, is there's this kind of nonlinear issue to it. You could just break that off, though. Probably what you'd want to do is you'd want to say it's been somewhat linear for the last 50, 60, 70 years or something, like mostly linear. Of course, there's a little bit of nonlinearity to this, if you talk about that, kind of leveling off. So there's issues with this regression. I wish they kind of phrased it a little bit better. So I would say see, this says yes, the relationship is not straight enough, which we wouldn't say. If there's a problem, we're saying no, it's not straight enough. Yeah, so you wouldn't say, yes, this is good, it's not straight enough. No, straight enough is a thing we need to meet. It needs to be straight enough. The more in-depth answer could be only analyze the last 50 years for a linear relationship to say what has been the linear relationship for the last 50 years, because you want the line to go through the middle of the data. The problem with this, we still have the graphic up, is down here at the bottom side, it's not going, like, who follows me that this line over here is mostly good because the data is around the line equally. That's what you want to generally see, and I know that's not perfectly linear, but especially if we go into, see, there's that bend there. That bend is bad too. That bend right there, we don't want to see. That's a sad face. What we want to see is you want to see this to where the data is generally above and below. You don't want to see these wavy patterns around the line. So this does have some non-linearity issues. I dislike at the start where they say general linear. It's like, well, what are you getting at? This one used to get me. Not today, Pearson. Not today. So we got, I think people are saying the animal gestation one next. That one has popped up a few times. It's another tricky one. Animal gestation one. Is this it? This is fertility rates. Is that's not the gestation one, right? I skipped one. Oh, I found it. Okay. Let's do the gestation one. 36, 23. Get myself an energy drink. So, happy St. Patrick. Hey, Colin. Not even kidding, Colin. We mentioned you at the start of class. I gave you the shout out. I should send you the video. But I gave you, Colin, the shout out right there. So, and we also brought back up this. So hopefully we see a few more applications today. We talked about Scott Daughtery, but you're at the start of class. Our shout out of the day right there. So I wanted to give some mentions. Thank you for sending this my way, and hopefully we get some awesome applicants to it. So check it out. If you haven't, Disney is taking applications right there for data in Disney. Check out the links I sent out. I'm kind of giving a, like, should describe it better. But loving some Disney right there. Extrapolation. Ooh, we love some extrapolation. Or we don't. Here, we'll retimestamp this. Okay. Here we go with, is there any evidence that an animal's gestation period is related to that animal's lifespan? So R, who can tell me from today's lecture, R is the value of what? I want a very specific thing said. R is the value of what? You still look young. In a good way, in a good way. If people say I look young, I'm very happy. Trust me. It's as soon as they say you start looking old, you don't get takebacks on that. It doesn't go in reverse. R is the value of correlation, sample correlation, sample correlation. Good answers right there. Matthew, throw you some points. It's R is the value of sample correlation. And with this right here, for this data, the sample correlation is 0.538. This is not, it's a moderate. Do you think the association would be stronger if we removed humans from this? So if you were to remove humans, what would happen to the correlation? So remember, outliers can dramatically impact correlation. So if you remove humans, the correlation would get wetter. So we're going to take humans out of this. We're going to say nope. And now we have that correlation. Because with humans, it would look more like this. We'll try to change the color. It'd be stronger, yeah, because humans are like making it less like a 1. The more, when you draw around it, the more it looks like a 1, the stronger it is. And if it goes up, +1. If it goes down, -1. So, yes, that is a much stronger correlation. Stronger, it's not because it's easier to fit points.
It doesn't matter!
Is the reason justified? Sure, just say we're doing non-humans. So restrict to non-humans. Yep. And then you get into a little bit of output right here. So here's the new plot for it. What are these values over here mathematically? See, now we get an R squared. What is the name of this value here? What is the name of this value? Now, it's calling it constant. They're trying to trick you. It's just a constant you always add to the regression model. This is the name of the x variable. So what are the names of these things? What is the name of that first one? 89 is the what? I wish they didn't call it constant, but they try to show you every which way you could ever see these things outside of this class. The constant is mathematically what? Very close, Soraya. You're very close. I think I know where you're going with that. Yeah, we could do that one too, Megan. You got it. I think I know where you're going with that, Soraya. Just a little more specific. The y what? I mean, I think I know where you're going. The intercept, exactly. It's b0, the y-intercept. And this is b1. For each additional life expectancy year, the gestation period is expected to last 13 days longer or something like that. So the first one's the intercept. The second one's the slope. So those are the values we get there in the corner. And let's see. The association is definitely positive. It's not perfect. That would mean every point's on the line. Moderate, strong, I would say. Moderate, strong. Interpret the slope in context. The slope is going to be the 13 because that's the B1. So that's B1 right there. And it would be on average for each additional year in life expectancy, the gestation period increases by, and then we just go 13.03 because that's the slope. A certain mammal has 28 years of life expectancy. So estimate the gestation period. So what do? If 28 is X, we have to write our equation. I think Joshua, you might be behind. If you hear this, Joshua, hit the live button. Be with us here live. So we have to do predicted gestation is equal to 89.7284 plus 13.0334 times X. So exactly. And then we just plug in the numbers. Does that make sense? We're going to plug 28 into there. So we just have to write the equation. They didn't ask us to, but we're going to write it. And we plug 13.0334 times 28 plus 89.7284. And that just solves the predicted gestation is 454. And do not round to one decimal at the end. There we go. And that's got it. We're on a roll. Yeah. And then Peel said, can we do the other one, right? Can you do the other question about animals and gestations? Yeah, let's find it. Is it... If you see the number, let me know. This is fertility. So this is not the one. If you see the number, let me know, Megan. Like if you're like, oh, it's number this. Is this it? This is it. I think this is it, right? Okay. If I'm wrong, let me know. But this is another question about... Yeah, cool. Okay. So let's do it. And once again, I guess I've already asked this, so I'll just answer it. We make scatter plots to visualize the relationship between two quantitative variables. So we should know that we're seeing a scatter plot. And it looks like there's some things. Don't want to... You got it, Zerai. I believe in you. Swing by office hours if you want. If you get something wrong, we can review it. Everyone, if you heard that, we do review things during office hours. If it is open, we can change it. If you come up here and do work in person in office hours, it's one of my things that I help you do the work. If we get something wrong, we usually fix it up to a certain degree. You can't just submit it and get a 0 and then I fix it. If you're up here doing work and you come here to review it, if it's open, you can't come and be like, hey, Brian, chapter 4 quiz from years ago. Yeah, no, it's got to be open. We work on it up here, and then we can make corrections. We can review it. So usually you get a little bit of a lecture from me. So you got to sit through the lecture to get the grade. Okay, we'll re-timestamp real quick. But swing by in-person office hours coming up a little bit later today. We can find the correlation by taking the square root of r correct, and then check the direction, though. Make sure to check the direction because correlation includes direction from years ago. I took this quiz 5 years ago, Brian. Sorry, you already graduated. Okay, so if we put a linear model to this, wow, hippos are way out there. Look at hippos. Just hippo doing hippos things. They're just way out here. They're a big outlier, so we'll probably see that come up in these questions. So let's see what the questions ask us about this. By removing one of these points, we could make the association appear stronger. Hippos. Removing hippos would make it appear stronger since hippos are more of a departure from the pattern. So I love to draw the regression line that helps me understand what's going on. Elephants are pretty much on the model as far as I can tell, and hippos are far away. You just try to put a line through the middle of the data. You can see hippos departs away from it. So removing that would make it stronger. Now, here's what's interesting. When hippos, is it pulling down or up the slope? By hippos existing, is the line being pulled down or up? By hippos existing, is the line being pulled down or up? It's being pulled down. So if you remove hippos, the line's going to go up a little more, right? So if you remove hippos, the line would go up a little more. Does that make sense? Because hippos is going to, it's like got a force. It's going to be like, yeah, I got to pull the line towards me. That's what it sounds like. And so the slope would increase. James, good to see you. Megan and everybody. Zariah and Matthew. Let's show you some points. So it would increase because the point for hippos is below the line. So since the point is below, removing it is going to allow the line to go back up a little bit. Should we just keep removing animals? No, you need a justification. See, this is a weird one. Let me read it. The true answer is no, you should we just keep removing animals to increase the strength of the model? No, you should only remove points that you have justification for removing. The second no, all data points for a model should always be kept. No, you can remove outliers, but you shouldn't just remove something because it's an outlier. So this is where I'm a little worried. I don't love their answers. The answer is no. Data points that are removed must be justified to be removed. That is the real answer. So the ones that's closest to this is you can remove something if it's not an outlier. If it's fake data, remove fake data from your model. The slope of the regression line is 15.5. If you remove elephants from the scatter plot, the slope of the regression model becomes 11.6. Do you think elephants was influential? Well, if it changes this much, then yes. Yes, because it lowered the slope significantly, so I would say it was influential in the model. Yes, because removing it, let's hope. Yes, okay, so that question right there. Yeah, I know, Megan, right? It's the way they say it. Is it possible to skim over the accompanying plot regression? My gosh. Yeah. Let's do it. I think people are doing really great on this quiz. Let's throw that one in here. Thank you, everyone, for being here. Brian needs more coffee. Am I right? One of these days I'll be able to see. I can't see. Look at all the ones we've gotten done. We're like over halfway done with every... Look at this. A variable that is not part of the model but affects the way the variables in the model are. What is this? Who knows what this is? A variable that's not part of the model but affects them is called a what variable? We did this earlier. If I see a quick one, we'll get it done. Then we'll do Matthews next here. A variable that is not lurking variable. Exactly. Explanatory is the X. Response is the Y. And there was another quick one back here. I don't know if it's super quick. Concert production company. So a point representing a performer who refuses to permit advanced sales. Well, if they refuse advanced sales, their advanced sales would be what? I don't think we have this one on our list. If they refuse advanced sales, their advanced sales would be what? If they refuse advanced sales, I'll put these in here as quick questions. Stat Tool 1, Chapter 8. If they refuse advanced sales, their advanced sales would be what? If they say, like, no advanced sales, then what? If they say no advanced sales, their advanced sales would be what? 0. So then you're extrapolating the model because you don't have data down there. So is far away from the other ones used to find the model for total revenue. Wait, a point representing a performer who refuses to permit advanced sales is far away from the ones used to find the model for total revenue. Therefore, the extrapolation is not valid. I think that would be right. Yeah. I was worried to get one wrong for the first time today. After Matthews, can we do is there evidence? You got it. Yeah. And so we got the accompanying plot. I was kind of doing those so that I know which one we've done. Look at this. Okay. Ooh, Matthews got a tricky one. I thought I heard something. Hearing random things. 49, 23. Get them. We might get them all done. Okay, so in this question right here, we are given a scatter plot. What is this in notation? What is that in notation? Who can tell me what these values are in notation? I want the notation of these, then we're going to write something out. So what we do a lot of times is we try to figure out what does the problem give us, and then we use it, and then we solve it. B0 and B1, Matthew, you're right for 5,000 points. This is B0 and this is B1. So you're going to do your y hat equals B0 plus B1x. And we're doing predicted, whatever that is. Oh, it's interest rate, I think. Predicted rate, I think it's the rate, is equal to 0.609. And we can carry the rest of the decimals as we solve this. Plus, that's, yeah, 0. 0.247 times years since 1950. So years since 1950. Years 1950. So we have to plug that in. Like if it's 1955, what would you plug into this? If it's 1955, what would you plug into the x? If it's 1955, you'd plug what into the x? If it's 1955, what do you plug in to solve? If it's 1955, you plug in what? Exactly, Matthew, you got it, because it's years since 1950, so that would become 5 right there. Good deal. Okay, let's solve this out now that we know what we got. What is the correlation? Well, first off, just do a plus or minus. Is the correlation positive or negative? Just positive or negative. Is the correlation positive or negative? Without even solving it, it's got to be positive, right? Because it goes up, so it's positive. And then r squared, you square root equals r, but then you need to look at the direction. So after you square root r squared, hint for the test, teaching you the test moment, always look at the direction or the coefficient of the slope to ensure that it is positive if it is positive or negative if it's negative. You turn it back to a decimal. It's a percent right now. Turn it back to a decimal, square root it, and there is the correlation of 0.88. So there's the correlation found from r squared, square rooting it. 2 decimals, correlation found. On average, the interest rate during this period has been increasing at about, and then we go grab the slope coefficient. How many decimals do we want? 2 decimals. It's been increasing by about 0.25. Ooh, that's a nice number. 0.25, starting at, and the starting is the intercept, 0.61. Now the real question, that's tricky. 2043. What are we going to plug into our model over here if we are predicting for year, and we'll write it in a different color right here. We're predicting for year 2043. So what will we plug into the model? In the model, we will plug in what amount? What will be plugged in for X? Remember, it's years since, exactly, Matthew. So we'll plug in 93. So we need to do years since 1950. So that's 93 years. God, it's coming up. My parents will be old, already old. And so we now take this data right here. The 93 we're going to plug in. Where's this at? Okay. So 93 times 0.24789 plus 0.6931. And there it is right there. There is the prediction for the year 2043. And this right here, I'm double checking. I think this is, yeah, sure, Joshua, we got it. I've got enough time. And that is going to be correct because it is percent like that. If you notice, it would keep extending and it would go up to about 23.66. Make sure to round to the right decimals. No, this is a huge extrapolation. Just take a look at the model. It ends after 30 years. It ends after 1980. We're predicting 2043, which is way far out. So this is a huge extrapolation. So just a ridiculous extrapolation. So that is no. The answer is no. And I think Zariah has the next one right here. Is there evidence? Do we have another? Ooh, is there evidence at which age? Oh, I think that one. I think this is the one also Joshua wants, right? So thank you both, Zariah and Joshua. I think we might get them all done almost in time. I might not have to stay over. Ooh. Get every question done. Okay. And let's we'll grab the question. Is there evidence in justifying them all? Okay, I think this is it. Yes. I think this is the one you wanted also, Joshua, right? Do age of... Is this the one? If not, we'll find it next. So this is currently 54, 53. Okay. Is there evidence the age at which women are getting married has changed over the past 100 years? I got married when I was 40, in my 40s. The accompanying scatterplot shows the trend. You got it, Megan. Shows the trend in age of first marriage of women. And let's look over time right here. So here is the trend. Is this linear or not linear? Also, look, the data was collected every 5 years. Is this straight enough or not straight enough? What do you say? Straight enough or not straight enough? Straight enough, not straight enough. Non-linear. There is, this is probably what we would do called a piecewise regression right here. Piecewise regression would be like you do a regression model there. You do a regression model here. Not like that. Do a regression model here. And you do a regression model here. So this could maybe be done with what is called piecewise. We don't teach it in 201, but there are techniques or nonlinear regression approaches like polynomial regression. This is definitely not linear. Also, there was gaps in the way they collected the data. They were only collecting every 10 years. If you look at the axis, they were collecting every 10 years. Then it looks like they went to yearly data. So just kind of what we can infer by looking at the graphic, the scatterplot, the visualization of two quantitative variables. So the trend appears to be nonlinear up to the 70s. Let's take a look. Yeah, 70s. So it appears to be nonlinear up to the 70s. It appears to be linear later on. This is ridiculously strong. Which of these graphics, graphic A or B, is stronger? You ready? I want you to write A or B in the chat. Which of these graphics, A or B, has a stronger relationship? Which of these graphics, A or B, has a stronger relationship? Yes, Megan, great answer. And don't worry if anyone says B. Don't worry if you say B. The answer is A. Strength is how tight the points are around the form. This has a nonlinear parabolic form. Don't worry, it will throw you some points. This one is weaker because the points are more spread out. The bottom one, B, is a linear relationship that's weaker. The top one, A, is a parabolic, super strong relationship. Strength is how tight it is. Association doesn't have to be linear. Exactly, a nonlinear association. Very great job, Joshua, and everyone practicing. So this is very, very strong because it follows very closely. There's very little scatter. It's scatter, which can be seen here, that makes it weaker. If you want to take a linear relationship and make it weaker, like here's a very strong linear, here's a moderate linear, and then here's a weak linear. If you notice, the scatter gets bigger. So the bigger the scatter, like this is super strong, this is moderate, and this is weaker. So the more scattered it gets. Remember, correlation only measures linear strength. So in good answers right here, so the correlation of this top graphic would be 0. That means this is weak. True or false? Correlation of 0, that means this is weak. True or false? Write true or false in the chat. Correlation of 0 means this is a weak relationship. True or false? Correlation of 0 means this is a weak relationship. True or false? False. Because correlation only measures linear strength. So strong relationships, don't worry if you got it wrong. If it's a correlation of 0, that means it only has no linear strength. Does that make sense? Correlation is only for linear relationships. Things can be strong and non-linear. So exactly, graphic A has a correlation of 0 because there's no linear relationship. It's very flat. If you put a line through it, it's very flat. So the correlation is 0, but it's very strong because it follows a parabolic form. So it's how tight it is around the actual form that denotes the strength of it. So just a big explanation to say that, yeah, this is very strong. Yeah. Is the correlation high? Probably not, because the whole graph is non-linear, so it doesn't have good linear strength. Correct. Strong is only how tight the points are around a form. Like, let me ask you this. You ready? This graphic I'm drawing here on the left, rather. Is this graphic strong or weak? Is that graphic strong or weak? Do these points have a strong or weak relationship? Super strong. Super crazy strong. That is a very, very strong relationship. But if you add a line to it, the line would go something like this. Because this relationship is very what? This relationship is very nonlinear, so the correlation of it is close to 0. Because correlation only measures linear strength. There's other forms of strength, like this is a sinusoidal strength. Think about a sine wave. That's what sinusoidal means. This is sinusoidal strength or kind of like seasonal patterns. This could be from the year, like how sales go or rainfall or temperature, things like that. Anything that's on a yearly pattern with a sinusoidal pattern where it kind of goes down in the summer. So this is a very, very strong relationship, but it does not have linear strength. It is not increasing or decreasing linearly. So remember, strength only denotes how strong it is around the form. So things can have a weak linear strength, but then a strong sinusoidal strength. So yeah, this has a strong parabolic strength, but no linear strength. So there's different types of strengths. Is the linear model appropriate? No, but you could put one later on. Yeah, there we go. Good question about linear relationships, nonlinear. So kind of like that. Look at this. Look at, we're almost there. Gallup smoking. Gallup on smoking. Smoking. Jim Carrey said that one time. I remember it. I was there. I was like, hi, Mr. Carrey. Say the line. Okay, here we go. The Gallup poll has tracked cigarette smoking in the United States since World War II. Now they need to track vaping. How has the percentage of people who smoke changed since the health dangers of smoking has become clear in the 20th century? Used to be, I think when I was a kid, when did smoking get banned on planes? When did they ban smoke heating expenses? Yeah. When did smoking get banned on planes? 1990? You could smoke on a plane in 1990? I was almost in middle school and people could be like, I smoke my cigarette on a plane. Is that smoke? I don't even know. I don't even want to smoke a cigarette because they wouldn't let me smoke it on a plane. That's why. I would have. Would have been on a plane smoking. Don't smoke on a plane. Okay. What a fun, like, pressurized cabin. Bad idea. Okay. So you see right here, office hours. If I can, toward the left. I have class. Yeah, of course. If I can. Yeah, we'll record it here, Zariah. So if you want to take it out later, I think that's what you're asking. Okay, so if you notice, there's a bit of non-linearity to this. It's a mostly linear, like this is all linear. That is crazy strong linear. And then there's a bit of non-linear at the start. So it kind of is non-linear at the start, and then it goes down in a linear pattern. So this is a moderately, no, the in-person, sure, yeah. So the percentage of adults who are smokers has decreased non-linearly between this and this. The decrease linearly from this is true. And then rose, no, it didn't go up. So this is wrong. It didn't rise. The percentage of adults who are smokers has stayed steady. No. The percentage of adults did not change much in the 70s. Yeah, that's about right. Where the number of smokers started to decrease dramatically and linearly until the end. That is true. The percentage of adults who are smokers decreased dramatically and linearly the whole time. No. This is a very strong association. The association is weak at the start, though. And if you take a look at this right here, Roto Wave Bomb, 5,000 points. We're talking about smoking and vaping Roto Wave. We're not endorsing either. This is where there's really no relationship, and then it gets much stronger because that's a flat line over there. So there's really no relationship at the start. So the association appears weak before 1970, then after. I wish they went into saying it's stronger. Is a linear model appropriate? No, a linear model would not be appropriate, although one could fit a linear model from the 1970s going forward, which is what we kind of did right there. I think we should be good. Get a little worried. Got 100. Got that hundo. We have gone without error today. What is going on? We have to make an error, right? Come on. One error during office hours. It's like we need to. And we're almost done with these. I think because these might be the last two. So if we get these two done and then we do the last one, except I don't have, there's no one I marked. Oh, is this one? Oh, this is the tough one I get wrong sometimes. After tracking heating costs. Okay, let's do this. Okay, you ready? Last few questions. Who's ready to get this done and do every question? Number 16. You know what you said, number 16? Let's do it now. Thank you so much, Megan. You're here. You get the 5,000 points. Let's put number 16. Let's get it done in institution reports. And the time on it is 1:05:03. Thank you, Megan, for saying that. That's easy when you see number 16. Boom. We can't avoid the inevitability of error. What's it? Is that Thanos? Uh-oh, Thanos here. Here we go. Take a look. We have a plot and then a residual plot. You notice the point over here that's really high. If you take and draw the line, they reverse it, which I don't love. If you take and draw the line through this, you will see that this point is dramatically above the line, which is this line right here. Well, rather, at 0 is where the line is at. Really? Sure. And that's what you're seeing. I wish they didn't reverse it. Some residual plots do that. Then you're seeing this point up here. This distance is the residual. So you're seeing this distance right here is that residual. And then you can see the large cluster of points over here is these, and that's what you're seeing in the residual plot. I prefer to make my residual plots where you make them flat. A lot of programs do that. It's most common. Some do this for their residual plots because there's like tons of ways to make them. I prefer just make the line flat. So with this in mind right here, we can see the regression coefficients. R squared, 66.3% of the variation in life expectancy is explained by fertility, or the variation in fertility. The standard deviation S is just the variation in the Y variable, just variation in Y, 5. And the intercept, when the fertility is equal to 0, we expect the life expectancy to be equal to 80.36, which is an extrapolation of the model because there is no fertility equal to 0. For each additional fertility, what does fertility mean? Births per woman. For each additional births per woman, we expect life expectancy to decrease by 4.7 on average. Are the conditions satisfied? We probably want to talk about this outlier. Other than the outlier, it's good. So the residual plot shows... Did they mention the outlier? The residual plot has much more variation. Kind of, not really. The residual plot shows strong evidence of nonlinearity. Not really. The residual plot contains clumps. No. I wish they mentioned the outlier. We're going to say it's reasonably good, except for the outlier. I wish they mentioned that, because a good residual plot shows no pattern. And if this was the residual plot only, that would be pretty good. Pretty good. We could go into advanced detail, but overall, that'd be pretty good. A perfect residual plot shows no pattern. That is a perfect residual plot. Perfect residual plot. Because residuals are what are left over. Not the regression plot up here. the residual plot to figure out what's going on. So I wish they said other than the outlier. Is there an outlier? Yes, at a fertility rate of about 7.5. So yes, where it's about 7.5, it's unusually high. And you can get 7.5 by going in here and just going between these. If you notice, you go right here and maybe it's 7.4, 7.5, but there should be some leeway on it. But that's right between 7 and 8. So, and it says to 1 decimal. Interpret the R squared, it would be 66.3% of the variation in life expectancy. And we'll put Mubot saying it here in the chat. It's blank percent of the variation in Y is explained for, which is like accounted by the variation, a regression model on the fertility rate, which they should have said fertility rate down there. So 66.3% of the variation in life expectancy is explained by the variation in fertility. That's what I would say. If the government leaders want to increase the life expectancy, should they encourage women to have fewer children? No, that treats it like cause and effect. So you wouldn't want the word cause or proven here. So although there is an association, there's no reason to expect causation. Lurking variables could be there, and we did get that hundo. I was a little worried, but you can't say cause and effect, and there could be other variables outside of this that are controlling it to a certain degree. Oh, man. This one, I know I've gotten it wrong before, so we'll do it. And then we'll almost have done all of them. You send this out and say, we did every question. Go on a quick walk in the cold. Do some office hours. Go home. Eat some good food. Exciting day. 109, 4-3. Okay. After keeping track of his heating expenses for several winters, a homeowner believes he can estimate the monthly cost from the average Fahrenheit temperature using the model. Now, notice this is a residual plot. So what this means is they made a model and then they plotted the misses of the model. So you have to be careful because the way their data probably looks is something. You see this line right here? This would be their model. And then the data goes around it like this, this, this. Notice I'm doing each point. I'm going to go below it again here, then a little closer to it, then 2 more below, and then 1 barely below, and then 2 more above the model. Notice how you can one-to-one track these points. Like if you go here to this point, these 2 points right there, I didn't want that color. If you go to these 2 points, they are above the model. If you go to like these 2 points, they are above the model. If you go to these 4 points right here that are below the model, or this whole section of data below the model is that section there. So this is the regression model. This is the residual plot. Nice job, Megan, getting that 100. We love hearing that here. So this is a residual plot of the model. So interpret the slope in context. There's the slope variable right there. Remember, your regression model is B0 plus B1x. And so when you do the slope, it's B1. So predicted value of y equals B0 plus or minus, whatever it is, B1x. So when it says interpret the slope, we are looking for this. So it'd be for each additional degree in temperature, we expect the cost to decrease by 2.08 on average. The model predicts a decrease of this in heating costs. Interpret the y-intercept. The y-intercept is B0. So the y-intercept is when x is equal to 0, we expect y to equal B0 on average. And we're trying to erase. There we go. And do remember, Mubot is going to put these interpretations in the chat. Slope, intercept, so you can read them as I say them. And the intercept is this one. So it's when temperature is equal to 0, we expect the cost to be 115 on average. So the model predicts a heating cost of 115 when the temperature is 0. So it kind of put it in 2 parts. During the months where the temperature is around 32 degrees, so would you expect the cost predictions based on the model to be accurate? Why or not? And so around 32 degrees, it's iffy. This is where they get me. See, are they talking about that one, which is slightly accurate? So the predictions are going to be higher, right? I'd expect it to be too high because the residual is negative. And well, it's still negative. Okay, good. So the model makes predictions here. This is the model predicting. These are the y hats. These are the actuals around 32 degrees, because 32 would be in here. So we would expect the prediction to be higher because the residuals are negative. So that should be right. That should be right. What heating cost does the model predict for a month that averages 10? Simply plug 10 into temperature. So we're just going to take 10, plug it in. And you can kind of see it now. We can't because that's the residuals. It's not the actual plot. So take 10 times 2.08 and then subtract this from 115. We're going to get like 94 or so. There we go. 94.2. I should have done that in my head. I could have. And now, during one of the months, which the temperature was 10 degrees, what were the actual costs? Now, this is where it gets tricky. Notice the residual is negative. So it's saying it was lower than predicted. And I guess they want us to do this right here. So if you think about this, since we know the prediction was 94.2, then what does this mean? Well, right here, would we include yeah, you could do that. Great job right there, Grace. This is 94.2 here. So then the residual looks to be about -1, right? Yes, -1. So the residual there looks to be -1. So that means the truth is 1 lower. So E is equal to -1 as best we can tell. And so if you say E equals, and this is the predicted, E equals actual minus predicted, and we know -1 equals, we're trying to solve for Y, 94.2, then when you solve this, it would have to be 93. If you algebra it out, it's going to be 93.2 because you have to get -1. So that's plugging in the numbers. So we were given, or we solved this from the last one with the y hat equals b0 plus b1x. That's how we obtained y hat from the last problem. And then we have to estimate E given this plot. So the E is being estimated right here, and that's how we get E. And then simply plug and solve for Y. Little tricky. So it should be 93.2. Do you think the homeowner should use this model? No, it's got nonlinearity. I think I think this might be the one I get wrong. We've done so well. We've got nothing wrong. We've missed nothing. No, because see, now it doesn't say nonlinearity, so that's scaring me. No, because units. What would this model be successful if created with Celsius? No, well, it wouldn't change it. Yeah, no, because units do not influence the accuracy of a regression model. Okay, come on. Is it that one way earlier that I said? No, what did I get wrong? It is decrease. We were so perfect today. It's not going to be that. It's not this, is it? Ooh, it's this one? Grace, did you see that? I had it. I put 93.2. Everything I did was accurate. I just didn't round the way they wanted me to round to. So everything was perfectly accurate. You're welcome, Zariah. I did it all. I got it right. I got it too right. And if you email me, if you make a mistake like that, please email me and say, hey, Brian, I did a decimal rounding error. And then we'll do this last one in justifying. This is the last one. We'll have done every single question on the quiz. Woo! Get them all done. Okay, so let's get this last one done right here. Then Brian's going to go on a walk and eat his sandwich. Got a peanut butter and jelly sandwich for today. Love my peanut butter and jelly sandwich. Okay. Last question of the day. All the questions in justifying his choice of a model. I know this model is correct because my R squared is 99.4. that tells you nothing about the fit of the line. Just tells you 99.4% of the variation in your y variable is explained by the variation in your x. R squared is not how good your model does. R squared is just the statistical fit, which doesn't tell you if the line is appropriate. It just tells you how well does the model explain it, which is good to have higher. Could I see 2 more questions real quick? I might. We've done them all. They're all going to be, let me say this real quick. If you're checking out this later, we probably have them all, James, right there. So check this out. I'm going to save this to make sure we don't lose it. But every question is listed, and the video will be posted here in just a moment when I end with these timestamps. But every question's in here. We've done them all, James. So does that work for you, James, right there? So every question should be in here. And once I end the video, it'll go up as a VOD. And then all the timestamps will be there. Yeah, so you get the benefits of being here. Awesome. Thank you, James, for being here. Let me throw you some 5,000 points. Appreciate it. I'm going to just head out and eat a sandwich before in-person office hours. So no, a high R squared does not mean the model is accurate. No, the scatter plot should be examined. So we don't just say because the R squared is high. And I only missed one thing because I didn't round properly. Awesome, Joshua, and great work. Hope you got that 100. Does the model allow the student to make accurate predictions? No, you would. Well, to a certain extent. Now I'm getting tricked. Can't get another one wrong. We got one wrong by accident by not rounding. So I know the model is correct because my R squared is 99.4. Well, that doesn't tell you. No, the scatter plot should be examined first to see if the conditions are satisfied. True. Does the model allow the student to make accurate predictions? Yes. I think it's going to be this. Because this one is wrong. A high R squared value always leads to inaccurate predictions? No. It doesn't always lead to accurate predictions either, because there's ways. You'd say, well, when might it not work? Here, we'll take a re-screenshot and I'll show you. Generally speaking, a high R squared is a good thing, because generally a high R squared is when you get this. And then the R squared would be something like R squared equals like 0.98. But you could have the instance where you have data that looks like this, and then you have one data point over here giving you a high R squared. So that could be an R squared of 0.98 also. So the model works really well on one data point, and that's causing the high R squared because of the leverage. We don't even get into leverage, but influential point and leverage is what's going on here in the advanced statistical idea. And so you can't say because the R squared is high, it's good. You want to look at the scatter plot. And there can be models that work for and models that don't work for. So they're probably going for, no, the linear model might not fit everywhere. Yeah. And that's true. The answer is just look at the scatter plot. You should look at a scatter plot to see if it works. Well, with that, R squared only tells us percent of variation Y explained with the variation X. We're going to head out, eat a sandwich, and enjoy the day, even though it's cold. Bye for now, everyone. Bye.